zk transactions. Okay, this is my lab and company. So we are mainly working on the zk-SNARK research, and also we are developing some zk-SNARK powered applications. Okay, so these are research topics. So if you are interested, then maybe you can read our papers. So recently we are working on the batch set accumulator membership papers to accelerate the membership proof in the zk-SNARK. Okay, so let me briefly introduce about the zk voting first, which is zk-SNARK based corrosion resistance end-to-end verifiable voting system on public blockchain. Actually, the zk voting is I think is the first voting system which is supporting the corrosion resistance and also end-to-end verifiability using the zk-SNARK on public blockchain. The voting system has to provide the ballot privacy, which means that no one knows who is the voter for each ballot. We are providing that feature, and also end-to-end verifiability means that all voters can verify that their ballots are included in the counting result. Okay, so we made this one using the blockchain and zk-SNARK and some apps. So our solution, our application is including the three parts. One is app, which is generating the transaction with the proof system. Definitely the transaction is encrypted. That is actually going to the blockchain, public blockchain. We test on the Ethereum blockchain and also Python blockchain. So we actually this is a service now, and there is some voting manager, which is a web server. So if you are going that zkvoting.com, then you can freely create the new voting, and also if you are downloading the app from the Play Store or App Store of the zk voting, then you can use this zk-SNARK powered voting systems. Because I don't have enough time, so I will briefly introduce these things and then I will skip the detailed one. Okay, so this is how the zk voting is working, so I'll skip this part. Okay, so this demo, if we are, okay. So maybe I can press this one, so this is quickly. So, yeah. So let me skip this part. Okay, so second one is Azeros, which is auditable generalized transaction is smart contract. So it is very similar to the Tornado Cash in EW. As you know that, I mean, Anthony from the Leo was mentioning about that the privacy is very important. Because if we are looking at the blockchain, then we know that who is the sender and who is the receiver and how much money is transferred on the blockchain. So it's very annoying that your information, privacy information is leaked. So to hide that information, the easy way is to encrypt the transaction. But encryption is not enough because encryption doesn't guarantee that the transaction is correct. So to guarantee the correctness of the transaction, we have to put the proof, general proof. So that's the mechanism of the zk-SNARK is working for the privacy preserving. But still, there is some regulation about the anti-money laundering in the blockchain things. So if we are using the Tornado Cash, for instance, then we cannot track the transition of the money, which is violating of the anti-money laundering system. So to meet the anti-money laundering system, we also have to trace all the transactions. So we are considering this privacy thing and also the auditing things. We create the Azeros, which is a privacy preserving token transfer, but auditor can trace the transactions. So which means that the encrypted transaction can be decrypted by the auditor. Okay, so this one is actually adopted in the Bank of Korea as a CBDC. So if the Bank of Korea is releasing the CBDC, then maybe you can use this other system. Okay, so this Azeros is working in the Quantum blockchain and also in the Ethereum. In the Azeros, there are two accounts. One is a public account, which is just like an external world account. Another one is an encrypted account. We are calling it as ENA. And there are two entities. One is auditor, and the other is just users. Auditor has a public key and private key. Using this auditor's private key, auditor can decrypt all the transactions to trace. Okay, so this is showing the overall algorithms. As you can see that there is a client which is generating the privacy preserving transaction. It is moving the money from the external order account and encrypted account and also commitment, just like zk-Cash. And using this zk transfer, it is also moving to the UA and encrypted account and also the commitment. Okay, so this zk transfer is actually implementing the private transfer. That transaction is moving to the blockchain. Then the blockchain is checking. Actually, the smart contract is checking that the validity of the transaction using the zk-SNARK. And also it is updating the Merkle tree because the commitment should be accumulated in the Merkle tree. Okay, so that's how this Azeros is working. Okay, so we are implemented and this, actually we have a plan to release this one on multiple chains. Okay, so this is showing the experiment of our Azeros. So actually we changed some hash algorithm. So basically we used the SHA-256 and also MIMC hash and also we used Poseidon. So we conclude that actually the Poseidon is best for the generating of the proof, but it requires more gas consumption because of the construction of the Merkle tree. Actually, if you are going to the imprint, then you can find this Azeros, which is telling about the technical details. So we are developing some app to utilize this Azeros systems. Okay, so last I'm introduced about the zk-Rollup for this Azeros transaction. As I mentioned, the Azeros is privacy preserving transaction, but actually it requires high gas consumption. So that is the problem. So here this is showing the Azeros. There are two parts. One is the client part and the other is the blockchain part. And the transaction is performed in the smart contract in the Elon smart contract. The Elon smart contract is verified proof and also it is updated in the Merkle tree. So if we are measuring the gas consumption for each one, then verifying the proof requires 400K gas consumption, and the Merkle tree update requires 1 million gas. It's really high. So we want to reduce these two gas consumption using this zk-Rollup. So we are using the zk-Rollup for this zk transactions. So we are moving that proof verification and also tree update into the layer 2. To aggregate the proof, we are using the SNARK approach, which is introduced 2020. And tree update, the layer 2, Rollup server is generating the proof, whether the proof is, the tree is correctly generated. Then layer 1 is just verifying the proofs. Two proofs, one is aggregated proof and another one is Merkle tree update. Okay, so this is showing the layer 2 things. Client is sending the multiple transactions. In our case, we are considering 2,000 transactions. So these 2,000 transactions are going to the server, Rollup server. Then Rollup server is aggregating all the proof, and also it is generating the tree. So actually update and generate the proof. Then that new transaction, for last transaction, is going to the L1, and L1 is checking the SNARK proof for the aggregate proof and also Berkeley tree update. Okay, so let's skip this part. Okay, let me show you the evaluation. As I mentioned, the one zk transfer requires 1.4 billion gas. So now it is reduced to the 0.0 billion gas. So we can reduce like 1/15th gas consumption. But the actual problem is that because we are regulating the 2,000 transactions, the one transaction of this large one consuming like 200 billion gas. So currently no blockchain is supporting this kind of large gas consumption. So maybe I think in the future there will be some solution for that. Okay, so this is demo. Okay, so let me conclude my talk. We are actually developing the three main applications: zk-ROT, Azeros, and zk-Rollup. I think all the application can be implemented into many L1 blockchains. So I think